Hey everyone, we are Alan Mai, George Hong, Griffin Palmer, Anthony Ayoung. So today we will be talking about multispectral satellite image classification with VGG16. First of all, after doing careful analysis on the topic of our project, we stumbled upon a type of convolutional neural network fairly new to the field of image processing, which is VGG16. We looked at a SAT4 dataset which comprised of satellite images from different terrains and trained it on a VGG16 model to classify what terrain a satellite image is showing. This will give us a further understanding on how well VGG16, pre-trained with the ImageNet transfer, learns from these images, as well as investigates ways to use multispectral imagery with VGG16. All this in hopes of one day help us further analyze environmental development and degradation. VGG16 is a convolutional neural network. It was the runner-up for the ImageNet classification in ILS VRC 2014 competition. It uses the idea of shrinking spatial dimensions but growing in depth. Keras has its own implementation for VGG16, so we will be using this for the project. One topic we touched in class was neural networks. Essentially, we learned about a system where the output stands for the next input. Hence, we have CNN, which is a type of neural network that is mainly used for image processing. But in theory, it should remain the same, meaning you have a set of processors working linearly until the last layer. One of the core differences that distinguishes CNN is the tendency for layers to decrease or shrink the deeper they become. Also, input goes through a series of convolutions and pooling layers. Here are some papers related to our topic. The first paper used AlexNet variations and VGG to classify SAT4 and SAT6 data on land use, in which they were able to obtain a 99.98 accuracy for the VGG. The other consisted of satellite images of the Amazon rainforest, which classified each one using VGG16. In this case, based on F2 calculations, ResNet 50 had a better score than VGG16.
We used the SAT4 dataset that contains satellite images of different land types covering California. The data consists of 28 by 28 pixel data, each pixel containing traditional RGB values as well as near-infrared values. The training set has 400,000 samples and the testing set has 100,000 samples, and both the training and testing set were previously split by the original owners of the data. The data is divided into 4 different classes, the first being barren, second being trees, third being grassland, and the fourth being any other type of land type that was not mentioned in the first 3. Before building out and training our VGG model, we wanted to get an idea of the distribution of the data. To do this, we built a histogram that shows the number of samples that belong to each class, and the histogram contains both training and testing data. So as you can see from the histogram, roughly 35% of the data consists of other land type. And this is more than likely due to the fact that other encompasses many land types in one class, whereas the other 3 classes are all single land types. So after we got an idea of the distribution among classes of the data, we also wanted to get an idea of what the actual images look like, since the original data set only consisted of pixel values. So what we did was we plotted the first 4 images of the data set, and to generate these plots, we pre-processed the original data to separate the RGB values from the near-infrared values, and then we plotted each respective image. And from the figures on the slide, the first thing you can notice is that the near-infrared images of the barren and grassland samples are fairly similar to each other. So next we had to pre-process our data because the original data set from Kaggle had RGB and near-infrared stored in one long array, and our VGG model required 3 channel image inputs with size 32 by 32 or larger. So first what we did was we reshaped each image to RGB near in separate channels. And from there we expanded each image without interpolation to an image size of 56 by 56 pixels, each containing the original 4 channels. Then we separated the RGB and near-infrared channels, leaving us with 56 by 56 pixel values containing the 3 RGB channels, as well as another 56 by 56 matrix of pixel values with the single near-infrared channel. Finally, we duplicated the single near-infrared channel across 3 channels to fit our VGG model and rescaled the image values from 0 to 255 to -1 to 1.
To set up VGG, we split it into its 3 parts: its input layer, its convolutional layers, and its fully connected layers. The input layer was modified to accept the 56 by 56 by 3 images of our dataset. The convolutional layers were initialized with the weights trained during the ImageNet competition. Then these layers were frozen to prevent modification of the weights while training. We also added 2 fully connected layers with random initializations with the ReLU activation functions, each with 0.5 dropout, which was the original setup during the VGG paper. We then added one last fully connected layer with 4 outputs of a softmax activation function for the 4 land type classes. We used the loss function of categorical cross entropy and atom with a learning rate of 0.0001 as our optimizer. We played around with SGD with momentum and nostril of accelerated gradient, but we found that atom resulted in higher validation accuracy. While the pre-trained VGG weights were for RGB, we wanted to make use of our multispectral data in the near channel. In Deeproot's paper, which also used VGG with RGB near imagery, they outlined 2 approaches to make use of this multispectral imagery. The first approach is early fusion, in which the input of VGG is modified to accept 4 channels rather than the standard 3. However, we did not implement this due to the complexity of the VGG model. The alternative approach is late fusion, where we combine the classification images of the 2 VGG models, one trained on RGB, the other trained on near, which is why we duplicated the near channels to fit the VGG input. In this approach, the score or probabilities of each class given a sample is the average of the score for that sample from each VGG model, one trained on RGB, the other trained on near infrared. However, this method requires much more memory and time compared to early fusion. In the end, we want to compare the results of VGG trained on RGB, VGG trained on near, and this late fusion approach.
One of the things we manipulated in our models was batch size during training. We tested it on an RGB model with 400,000 samples and 4 epochs. We can see that a batch size of 256 has training time of 57 minutes and 32 seconds, a validation accuracy of 98.618, and a loss of 0.03948. In theory, larger batch sizes require less iterations due to a more significant gradient, but lower batch sizes are less computationally intense due to the smaller size. It seems that the training time was not affected as much by batch size than other factors. The loss and testing accuracy both got worse as the batch size increased, but it does not seem to be very significant at this level of size difference. We might possibly see more model depreciation at significantly higher batch sizes, like around 50,000. The metrics we used were testing accuracy and F1 scores. RGB had the greatest overall accuracy at 98.785 and the best F1 score at 0.9858. Near infrared had lowest accuracy, and we can see more in depth about how our models performed in the next slide. This slide shows you visualizations of confusion matrices for each model. The columns of the confusion matrix will tell you the true values for each class, and the rows tell you which classes were predicted. The values are normalized so that it shows a percentage of how many were predicted for each class. If you look here, The near-infrared matrix will show you that 5% of grassland samples were misclassified as barren. That same model shows you that it had trouble classifying between barren and grassland. This was due to near-infrared being grayscale. This means that barren land and grasslands are similar due to having no significant features. We can see on the top left that the late fusion matrix has the best accuracy for barren and trees while having a similar performance for other, but the grassland issue carried over from near-infrared. Here we can see an example of the RGB and near-infrared of all the classes. You can see that the near-infrared for barren and grassland look very similar, and this causes issues with VGG. This is due to the convolutional layers trying to extract features into feature maps. However, both barren and grassland don't have many features to extract besides color and slight terrain textures.
The biggest takeaway from our project was the idea of memory management with large data sets. In the beginning of our project, we had an extremely difficult time uploading our entire data set and using it to train our model because of how large it was. However, we learned that reading data in chunks rather than uploading the full data set at once is much more efficient. We also learned that training and optimizing deep and complex neural networks with large data sets takes a very long time, so it is extremely important to start early when you're working with deadlines.
In conclusion, we found that VGG with transfer learning performs very well for classifying the satellite images. However, it does take a long time to train. More specifically, we found that both RGB and near transferred well, with RGB having the edge in both accuracy and F1 score. While we did end up having great results with the transfer learning, we were not able to replicate the results of previous paper. This could be a multiple of factors, including using late fusion rather than early fusion like the paper, not using the full 224 by 224 image size that ImageNet was trained on, or other training optimizations in increasing the number of epochs used while training. However, we did find that late fusion with RGB and near had the potential to perform very well, but will still need follow-up in the training of the near model. For follow-ups, we could correct the image size to 224 by 224 to get the most out of the pre-trained ImageNet weights. We could train longer with more epochs. We could use early fusion with RGB and near infrared. We could use more refined training techniques such as decreasing learning rate after a number of epochs, or unfreezing the convolutional layers after a number of epochs. Or we could use different weightings in late fusion, such as having more weight emphasis on RGB, or the weights between RGB and near could be trained while training.